Okay, hi, welcome. I'm gonna start this because there's no reason to wait for them. If they come, they can join, and that's all. I think there are a few on the net, maybe. If not, I'm gonna start. I'm gonna speak in English because it's broadcasting, and because this is not this was planned to be organized in a wider audience, and this would be the first rehearsal. I'm gonna present here in iQuest. If it turns out good, then I'm going to continue and maybe hold this for entire Cluj, something. Yeah, welcome. And reactive streams. Let's start. Yeah, this is the live stream link, which is not very helpful for you because you are already seeing it, but maybe you can tweet it or send it or share it, or I don't know, call your friends and spell them hunorkovacs.com/reactive streams, which actually I forgot to activate it. It should redirect to the live stream. Hashtag is reactive streams. My username is Kovachuni on Twitter or anywhere. Okay, reactive systems. Let's talk about first what are reactive systems. Reactive streams is a part of reactive systems. Well, this notion was defined by a few people. This Causing Netflix, Pivotal, Red Hat, Twitter, TypeScript. These are companies who are trying to agree how to revolutionize software engineering and how to create programs and applications that are very efficient and fast and reliable. So these are the main keywords: responsive, resilient, elastic, message driven. I'm not going to enter in each of these terms, but they are described very well here in the Reactive Manifesto. They are all written here. I'm going to come back to this later, but I'm running against time. I'm going to start this timer now because there are a lot of things that I have to tell you, and there's no time. I wanted to shorten this presentation very, very, very much so that you don't phase out like 20 minutes, 40 minutes, but I couldn't make it, and there's so many, and still you're not gonna understand even this way. But okay, so I arrived to this part where I'm gonna start coding. It's going to be a bit odd. I'm gonna code first and talk after. Okay, so don't worry if you don't understand something. You will in time a little bit later. So here I have a project which is almost empty. I have just one class here, but this has only to do with measuring some things. I'm going to show you graphs here. This is a graph. It's flat, not seeing anything right now, but later you will. So this is an almost empty project. I'm going to start out. This is written in Scala language, and the whole reactive streams thing would be wider than that. It's not just Scala or not just akka. Akka is the library. Scala is the programming language, and I'm going to code in that, and I'm going to show you in that. This is also doable in Java, and the reason I'm doing it in Scala because this way you can see at least even more. You see how Scala is. I know not very many people are familiar with that, and maybe you can just have a glance at it. Yeah, other than that, reactive streams is even wider, should be even wider. They are trying to develop the whole concept for any language and even protocols like TCP. Okay, let's start. I'm gonna intro. It's a Scala class. Even better, let's make it an object. Object is a singleton class. In the meantime, I'm gonna just throw in some explanations for some things. Maybe you won't understand everything, but just try to bear with me. If I extend the app object, then this whole thing is like a public static void main. Is everything I write in the body is going to be executed. Okay. Source. I'm going to define a source. Is a is something that from where data comes out. So it's something from where bytes or anything flourishes out, and you don't have to know what's even deeper. Source could be from a file, could be from the network, could be from a collection or anything. Here I'm going to use an iterator continually and 0. So what this does is this creates an iterator on which you, whenever you call next, it's going to return a 0. So this is an infinite one, and source is going to source its data from this iterator. So this is an infinite source of zeros. Okay. Sync is the opposite. Is something where data goes in, and the whole flow ends there. So can you see what does this create? So you have a source, you connect it to a sink, and you have the whole thing. A stream is like that. For example, at the television show, you have a or I don't know, for example, a news broadcast is a camera. That's let's say the source, and it goes through satellites and goes to your home. On your TV, that's the sink. It's a monitor. You see it, and that's all. That's it. Okay. So I'm gonna just write ignore. This is a thing that ignores data, so you don't do anything with that. Just to be very simple at the beginning. Okay. Source to sink. Okay. Flow is an aggregated term that refers to anything. A flow could be flow is something that has an input and an output. So a thing just has an input, a source has just an output, and the flow has both ends. You can connect stuff. You can connect flows together, and for the start, you put a source and a sink at the end, and the data flows through them, and they modify it. They just transform the data. Runnable flow is when you always have a sink and a source. So a flow is only you can have elements and hanging in the air that it's not runnable. If you connect them together, you have a complete circle. Then it's fine. Runnable flow dot run. So this would be the app. Okay. Now I have a few boilerplate things to do. Even this is Scala, and they are advertising this because advertising it with saying that it has less boilerplate. We still need something, and this is very hard to explain for someone who hasn't dealt with actors and the whole akka library. But let's say this actor system is just helping us with threads and helping us running the thing. It's an implicit variable, and we need an actor materializer. Yeah, just ignore this, okay? So this way, I think it should run, okay? Let's try that. Just a second. Okay, it's running. I check my activity monitor, and I'm seeing a Java app which is running too fast and burning my processor. So I'm gonna stop this. This is like an infinite loop. I think you can imagine that this infinite source of 0 going to nothing is just very, very fast. Good. Now I'm gonna just continue. Do you want me to explain this, or it's no? Okay. Instead of, let me check the stopwatch. Okay, 6 minutes. It's not bad. Instead of 0, okay, I'm gonna complicate things. Var I is a variable, okay, and I'm gonna return I. It's like in Java, return I is the same. In Scala, you don't need a return statement. You just whatever you put for anything's end, that's a return value. So it's the same. We're gonna sleep now. I don't wanna kill my processor. I wanna see also stuff. Sleep 50. And okay, now again a little bit of spending time on writing stuff. I'm gonna want to measure this. Okay, I wrote this influx thing here. This is measuring stuff on my graph, but I need to send it the message. So whenever this iterator produces a 0, I'm gonna send a message to influx. So it's gonna be like a send to influx, and I'm gonna send it a message. Okay, this is read yet, but I'm gonna do this. Private var. That's an actor. Okay, I'm not gonna enter again what's an actor, but actor of props. So I have an actor here. I can send an actor a message. I'm going to show you a bit influx. This is an actor. It receives stuff. It receives objects of type metric and of type write. Okay, let's go back. So I'll send it a metric. Metric is a small object I defined. You can see it here. It's a line, it's a string, and a long. It's the time when I do it. So I'll go and define well now is system current time and current time. No, okay. Okay, how weird is Scala for until now? How weird is it? Is it very weird, or can you see? Okay. This is the format I'm going to send the message. It's not important, okay? Also, I need something with which I send the data. That's going to be an inbox. It's an object that can send and receive data for actors. Private var val. This is also val. Val is a final variable. You can modify. It's like in Java, the final keyword. It's an inbox. This part takes a bit long, but later I'll write less. I have the inbox, send. Okay, and there's too many parentheses here. Okay, send, return, sync. Okay, let's run this. Okay, it's producing. So on the graph, you should see the producer is doing like 40, almost 40, 37 messages per 2 seconds. I could define this graph like that. So it's counting the values in producer and over a time of 2 seconds. So if you compute that, that's going to be exactly this thread sleep. Okay. I'm going to do the same thing for sync for each. And for each element that comes into the sync, I do something, okay? I consume them. I do the same thing. I want to measure that. So, but I'm going to be a slower consumer, okay? So this is a producer that produces elements every 50 milliseconds. This is a consumer that can consume them only in just half that speed. Also, I don't have to define I because it's defined, it's coming in, and I don't have to return because this is a consumer. I just ignore it, but I measure it. Let's run. Okay. Okay, so they are running at the same speed, and it's only 20, which is the 100 milliseconds if you compute it. Which means what I wanted to show you is this is the back pressure that this presentation is about. It's the streams that are reactive and they are doing computation based on the slowest element, so slowest part of the whole stream. So now the consumer is slower, so the producer won't produce more. And there's no buffer in which you have to aggregate and accumulate all the data that you can't process it, and maybe you don't have memory, and maybe it's not just zeros, but it's a whole movie coming in, and you can't process it. You have, I don't know, you have a video processor, you have to apply a watermark on it because you're a television company and stream is coming in and you can't do it fast enough, then it's maybe not the best example because the television stream has to go in the speed that it's broadcasted, but something else. Think about something else. Okay. Cool. A little bit of refactoring, all right? Because it doesn't look very nice now. Check the time. 50 minutes, okay. This has an inbox. Measured received as constructor parameters, a system, an actor system, and a influx, which is an actor ref. It's not going to be I didn't write here the class for influx because actors are separated and decoupled from the actual classes. You don't have to interact with the classes. Actors could also be remote. So if you set up a cluster, actors can run on separate computers, and you always have the reference. If you have a reference to an actor, you can just call it, send it a message, and it will it will land on the respective machine in the respective actor, and it can process whatever it has to do with that message. This is protected because I'm gonna do it like class producer spans measured. Okay, it has the same constructor. Oops. And this is like the super thing, okay, in Java. You call the parent constructor the same way. Yeah, here you have a produce function, which is this. All right, and I have a consumer's val. And the slowing consumer. This is gonna consume an I int. This is it's nicer than inline, right? So that's why I'm doing so. It's more understandable for you too. It's nicer anyways. Producer equals new producer, and it gets the influx and the system, and the consumer, new consumer, influx and system. Maybe okay, it's a normal consumer, a slowing consumer. Okay, slowing consumer is just a bit slower. It's gonna sleep t, and it's gonna add to that, so it's t plus 1 every time until t is lower than 400, let's say. Great. Sorry. Okay. Am I doing it right? 50. This has to be, let's say, 100 or 80, 70. Flowing is from 100 to 400, okay? Intro, okay, I have a consumer. So I'm gonna shorten this. So I don't even define these values because I use them only once. Continually of the producer, produce. And I'm gonna just run with sync for each. And I'm just gonna say consumer, consume. Okay, I don't even have to say in parentheses what's the parameter because this function is doing that, and it checks for this function whether it has the signature of an integer. So it's nice. And delete this. Oh. Funny. Okay, producer, consumer. Let's see. Yeah. Consumer slowing down, producer slowing down. That's how it should be. Stop it. A little bit of theory, okay? I'm gonna jump out from code, clear some stuff for you. So, how does this differ from normal way of programming? Because maybe you don't even know what's this reactive streams. So maybe you are associating this to Java streams, which would be like a list of 1, 2, 3, 4, 5, okay, and you call it, I don't know, a map function on it. So you map each element, you map to e+1, okay, and you do, I don't know, a filter on it for example every even element, okay. How is this? Like that. Okay, and this is going to return another list which has only those elements. This is like the Java streams, okay, in Scala, but it's not what I'm talking about. This is blocking, and the whole idea in this thing is that it's not blocking. So I'm going to explain. These are functions, and elements are coming, and you have to apply the first function and then apply the second and the third, and only if you have the third one, then you release that data and let it go. And until then, maybe there are other elements that could be processed, but you are doing it only in one thread, so this second element will have to wait until this is done in the whole thing. Okay, now let's say this is slow. The second function is maybe some arithmetic computation or whatever network, maybe send it somewhere, receive something for it, and that's slow. But these are fast, and this could go faster, and this is slow. That's fine, because as I told you before, the slowest link in the chain is whatever determines the whole flow's speed. But the thing is that the thread blocks. So the thread that comes here blocks and is blocking the whole thing. And you would like to use all the threads of your processor. So okay, so there are other solutions. For example, let's say this one. You have each computation done separately, and you push the whole stream, you push the whole data through it. So first comes, I don't know, a whole movie of 1 gigabytes, and you process it with the first element, and then you have another gigabyte, and this goes on. It's also not the best. I just thought I'll draw some bad examples here. There's a better one with queues, let's say, okay? And these computations go parallel, let's say, on different threads, different processors. That's nice. And you connect them with queues. So the elements come and queues fill up. This is slow. This queue fills up. These are usually blocking queues, right? So it has a size, and after that size, it can't accept more. And it's not going to blow, but it's going to block. The blocking queues work that way. If you want to put more than if it can hold and it's full, it's going to block that thread. This function won't be able to finish. It has finished the actual work it has to do, but it can't insert in the queue, so it's just going to block, and that thread's going to stop. Then this queue is going to fill up, and so on. So whenever you have the slowest element, the rest of the queues, they all block, and everything blocks. So we, I think, arrive back to this situation almost, or yeah. It's anyways a little bit better because you have queues and have these buffers, but it's not reactive streams is done with a little bit more complicated communication between these elements. They are signaling each other, and it's based on demand. So this is the sink, and it's saying, okay, I'm a sink, I can receive anything, so just give me. This receives that message and says, okay, I'm a function, I'm not full, I'm not processing, I'm free, so send me. Comes this one until the source. The source says, okay, you want data, here it comes. Reads from file or from wherever the source is defined. Data comes in here. Let's say this function is slow and it's blocking. This says, give me more. This says, give me more, sends it to here. And this guy says, okay, they are asking from me more data, but I can't process even the amount I have. So it's not going to propagate that message and not going to ask for more. So this is not going to get demand, and this is not going to receive demand, and the whole thing is not going to eat memory or processors. Here, these functions will not block the thread. So whenever they finish the computation, they say, okay, now I'm free, and I can do other stuff, maybe in another stream, or do other computations in separate parts of the program, or other programs on the same machine, wherever they have to go. It's not blocking the thread. Okay, it's all non-blocking. That's the whole thing in these reactive streams. I'm going to continue writing code. Okay. Okay, Tommy is asking, does this work on multiple consumers? What do you mean multiple consumers? Yes, that's what I'm gonna show you. Streams are not always linear. They could become very complicated. They could spread. They could split up in two streams, or even merging in from many streams into one. Loops in graphs, and that's what I'm going to show you right now. Okay, I'm going to define a balancer. Okay, def balance. It's a function. Okay, I'm going to define a function. Balance. Please balance me this stream between workers. That's what I'm doing. Okay, it's going to have a type. I mean, two types. In and out is the type of data that goes in, and the type of data that comes out is going to be int. But for the sake of complicating things even more for you, I'm going to write it in typed, or what's this, generic workers. Okay, between these workers, I'm gonna distribute the data. That's gonna be a list of workers, right? Worker is a flow. As I said on the beginning, it's an element which has an input and an output. So there's going to be more workers. The data is going to come in, spread between workers, and after they've done the work, they're going to merge it, and I'll have the one output. So this is a list of flows of in type, out type, and unit. The third parameter, don't ask me. Okay. I have to import some stuff. Akka-stream. Let's check the timer. Probably I'm off the time. Okay. Akka-streams KDS dot flow graph. implicit all. Okay. I'm going to define a flow. So this is the last statement from this function that's going to be returned. So balance is this function when you call it for a number of workers, a number of flows, it's going to return one flow, incorporating all these flows, connecting them through in a way. Okay, builder add. I'm going to add a balance. This is predefined. So the guys doing this library were kind enough to create us helpers and a sophisticated way to deal with these streams. In, out, don't even know, and worker size, because this balance just receives as in the constructor how many outputs does it need. It's like a broadcast, you know, on one input, many outputs, but it's not like a broadcast that is sending everywhere. It's sending to only one place, and it's smart enough to decide where to, where is the most free. Okay, I don't know if this comes here. Okay, balancer equals var. Builder add. I have a little bit of cheat here. Balance in. Yeah, that's right. So worker size. Not here. Here. Okay, val merge will be a merge which has separate inputs and one output, and it's gonna all send all the data that comes in from any of these inputs is gonna just send in the output. Each of these elements have their own rules of back pressuring. So, for example, if you had a broadcast, if one of the output would be back pressure, you can't receive input, because in a broadcast you have to send to everywhere, and if only one node can't receive, the whole thing gonna slow all the receivers. This is a balancer. Is different. If one back pressures, the other ones may receive more if they can. Out and workers size. This is the number of inputs it will have, and the whole definition of the flows in and outputs is going to be the balancer in, and the merge is out. This will be the input of this whole flow and the output of the whole flow. And I still haven't connected them. So what I'm going to do is like this balancer is going to connect to worker 1, okay? And after it's done, it's going to connect to merge. And the merge is going to, its output is going to go out, okay? And going to do the same thing like worker 2. And you can draw graphs like that here. You can also write merge goes also into, I don't know, another flow, and that goes into back to worker 2. If this would be valid, and they would have the inputs that I'm writing here, because they don't have all the inputs and outputs. Merge has only one output, and it's here. Yeah, it has this output. It's the same. It could go in another flow, but this flow couldn't go in worker 2 because worker 2 is already connected. But if you would like to draw something, it's possible. So the guys here defined a very nice way of drawing graphs and directing streams. How I'm going to do this is workers for each. It's going to be a balancer, connects to the worker, and it connects to the merge. Very short, and maybe for newcomers, it's not that understandable or clear, but this is short. We have the function. I'm gonna continue. So I'm gonna call balance for a number of flows. I don't have them yet. So consumers is a list of new normal consumer influx sys. This is a list of consumers. Private val consumer flows, because these are just consumers. These are classes, okay? These are not flows. I'm going to create flows from them. Is consumers map. For each consumer, I'm going to create a flow. So when any element comes in that in this flow will be consumed by the respective consumer. And I'm going to do this function for all of the consumers. So this consumer flow is going to be a list of flows, okay? And now I can use this and send it like via, sorry, here. This receives a list of flows, and the balancer is going to come here. Don't need this here now. And this is still missing here. Rate consume. This is an interface, okay? Hopefully everything's compiling. Should run. Let's see. Oh my god, it's running. Let's see. So what's happening here is that the producer is doing the best, and it can produce at its full speed because there are two consumers now, and I set the values to. I was at home measuring these values and choosing specific numbers. First, at the start, the consumers are running fast, and each of them receives the same amount of data. And with the power of these two consumers, we can deal with all the data. Okay, but one starts to slow down. It means that the other one has to take more. It can, and it's going to take more then. And this is going to continue until the point until this consumer slows down that much that this producer can take more of its load because it maxes out, means that the producer can produce that much, and that's going to decrease. Okay, on a long enough timeline, let's say 5 seconds. It's a nicer graph. Let's see it in 2 minutes. It's visible, right? So the producer slows down after some time. Check time. It's good. Haven't shown you the balancer. I'm gonna the buffer. It's another thing. Come on. Oh yeah. Buffer is just a place where you can buffer in some data, and if it fills up, I'm gonna apply this back pressure. So let's run it. I'm curious because I haven't done this way with these two consumer. But it's basically the thing that the producer is able to produce even that the consumers, if they were very slow, the producer would be able to produce at full speed until the buffer fills in. And when the buffer filled up, back pressure is going to apply to the producer only at that time. Here it's not very visible because at the start both the consumers are powerful enough to deal with all the data, so you won't see it won't see it in action. But I don't know, I can just maybe delete one consumer from this list. See, producer is higher than consumer, and this is going to hold up only for a finite time until the buffer fills up. See, from then on it's going to go just in the old way, the consumer speed. Now this would be it. Whatever else I want to show you, I could show you akka HTTP. It's the same thing going through HTTP. So an application producing and another application consuming, and the request going through, and the same thing with back pressure. But I think I can ignore that maybe, because you could imagine. But the same thing works for HTTP and through TCP as well. So let's continue with a little bit of talk. These are two websites, the reactivestreams.org and the Reactive Manifesto. Both are just a short definition of what it is and what they are trying to achieve in our world. The Reactive Manifesto is larger, because this is not only about streams. It's about the whole idea of doing and processing asynchronously messages, futures, being as flexible as we can and as fail tolerant as we can. These are a bunch of links. Yes, we have a question. Okay. Well, the one that I said was the blocking thing, that stuff are eating processor, and they are eating it in vain, because they are just blocking one thread and not doing anything while waiting for others. And this is one reason. Okay, I could show you something else here. Regardless of streams, for example, if you have one computation and another one and the third one, okay, and there you expect the result, okay, like result equals C and something like that, right? Is V2 equals the B function applied on V1, and V1 is applied to V0, I don't know. So these functions, and they're defined in series. And let's say if this is slow, when you go with the debugger, how do you do it? You go this line, it's done. You go this line, it's done, and you have the result. This could go in parallel, but if you have to define it, you would have to write threads, runnables. You have to define the whole while loop in them and synchronizing stuff. While, for example, in akka, there's a way, if you define a future, you do it like that, and it means that this result is not going to be exactly future of, let's say, this is a function which adds to x, it adds 1. And I don't know, okay. Okay, it's still not okay. So whatever. It's going to just return a future, and it's not blocking. So this is not going to execute the thing in that moment. It's going to schedule it for the actor system. It's going to schedule it in the processor, but it's not executed in that moment. It means that it can also schedule this one and schedule the third one. And only after all the schedulments are done, it's going to execute it in the way it wants, or it is allowed to. And these futures, these threads can go in a way, in an undetermined way, but in a more efficient way than blocking. I don't know if you understand this. So these are gonna execute in parallel if they can. Of course, this function requires the input of v1, which sort of blocks it logically, right? Because until we don't have this value, this can't execute. But let's say it's not depending on this one. Maybe it's depending on v88, which is not defined here. Okay, so these two could execute in parallel, and the whole akka actors and futures are built around this thing that things could execute asynchronously, and you can combine them at the end. Okay, because until for the end you'll need the value, you need the actual data, the result. But until then, you don't have to tell the program how to do it in what order. It can do it in the order it wants to, and it will do it efficiently. So streams would go the same way. You just defined how are they connected, and they execute as fast as they can and as efficient as they can in a fuzzy way. So all this reactive manifesto is about this. There's also message driven, which relates to actors, which I was talking about here in Influx. This is another way. This is not with future, but with actors. Actor is a it's a sealed thing, and it's thread safe, or how should I say? It has a queue of messages that it can receive messages in the queue, and it's just gonna execute the defined functions here based on what messages it receives. But it's non-blocking. Sending a message is fast. It's like, okay, you got the message, but then do what you want with it, but I don't need the result now. If it wants, it can send me back a message if it's written that way, but it's all loose coupled. Okay, back to here. The few links. This is the source that I was writing right now. These are the slides. akka.io. This is the company, and I mean the library. TypeSafe is the company. If you want to start out writing code like this, you can start here. They have a nice platform for it, like tutorials and stuff. Language is Scala. Let it crash. These are news about this kind of stuff. The same presentation that I was doing, there's a similar one here on YouTube. Another article. And for non-coders, this is just an interview. And I think that's going to be it. Thank you very much. It's 4 o'clock here, so I finished in time, ignoring only one chapter with the akka HTTP, but maybe some other time. Thank you very much. And I'm going to stop the broadcast. Bye.